Okay, let's continue. So let's start with our lecture. Today we are going to talk about summations, sums, products, and asymptotic. And we will see actually that these materials or this topic has something also to do with sequences. We have already, you have already seen, you are supposed to have seen uh, uh, sequences. A sequence is basically a list of elements, a list of components, and this list of components can be finitely long or infinitely long. Now, if it is finitely long, you can always list them, so you can basically show them in a table. But if it is infinite, then sometimes you will use ellipses. Yeah, for example, you will say 1, 2, 3, and so on. Now, in and so on is actually something really dangerous because we don't really know. There is no guarantee, and we don't really know what is the next components. Yeah, and summation is basically when it is used when we sums these components, and these components can be, like I said before, finitely long or infinitely long. We're going to see the summation, how to deal with the summation, how to basically solve them. And then we will see later on that if you already know summation, then products is actually is something really similar. So you will be able also to deal with products. But sometimes you will not be able to solve, to find the approximation or to find the closed form solution of summations. If this is the case, then sometimes it is useful to use asymptotic notation. We're going to see asymptotic notation. And this asymptotic notation also we're going to be useful for you in uh, algorithm analysis. When you are analyzing an algorithm, there will be a lecture, a course later on, an advanced and a more advanced course uh, that will deal with this basically. Yeah, that will deal with analysis of algorithm. So let's continue. So summations and products is something that will appear often in analysis of algorithm in many other fields in computer science. There are three possibilities. There are three possible results when you see a summation. Yeah, the first one is this is the best one, of course, because if you were able to do this, then the whole thing basically match. The whole thing is basically solved. The first one is called closed form solution. This is when a summation produce exactly a formula, and this formula is closed form. What does it mean by closed form? Closed form means that there is no summation anymore on this formula. This formula consists of only of variables, and these variables can be easily resolved to find a particular value. So if you know, for example, n here, for example, n is equal to 10, then you know right away that by replacing n with 10, the whole thing can be resolved, can be evaluated to some particular value. This is the best result, basically. So if you have a summation, for example, here, a summation from I equal to 1 until ni is equal to n multiplied by n plus 1 divided by 2. Now, why is it important? Because basically the complexity of performing this summation becomes really low, becomes even constant. So, for example, if I ask you to sum from I is equal to 1 until 10, then if you program this in a computer, then you will perform a loop, adding 1 plus 2 plus 3 plus 4 and so forth. So well, it is easy to see that you will need n steps to do this, because you are basically adding 1 to 2, so there is a summation there, there's an addition there, and add again to 3, add again 4, and again 5, and so forth. So you are basically performing n steps. Yeah, but if you know the closed form solution, then you don't actually need to do this looping. All you have to do is just evaluating this formula. And evaluating this formula is easy, because what you have to do is just n plus 1, this is one operation, multiplied by n, two operation, divided by 2, three operation. No matter how large n is, you are basically will be able to find this closed form solution in just 3 operations. Yeah, I hope that it is clear. But sometimes the problem is, it is not always possible for us to find the closed form solution of a summation. Sometimes the only thing that we can do is to approximate it. There is no closed form solution. It has no closed form solution. In this case, sometimes we are able to try to approximate. Approximation basically means that we will not be able to find the exact solution, but we can approximate it. We can be as close as possible as we want. For example, this is the Stirling formula for factorial, and the Stirling formula for factorial is n factorial, and factorial is basically is equal to 1 multiplied by 2 multiplied by 3, and so on, until multiplied by n minus 1 multiplied by n. And we denote this by this one. So if this is sigma here, sum, this is pi.
Sir,
Pi basically product.
excuse me, sorry for
Yeah.
but sorry for interrupting, but your screen is, black. We can't see anything.
You can see anything right from the beginning.
Yeah, yes, sir.
So
I can see
this,
the screen.
this haven't. Okay, so let me try again.
Okay, thank
What
you.
about right now?
Yeah, that's better.
Okay, so I see. So I will not be able to use the use the full
Yeah, we
screen.
can see
So
it
the
now.
problem is the full screen, I think.
I see.
Yeah.
Okay. Thank you,
Okay.
sir.
So yeah, let me restart again. I mean there hasn't been any slide. I'm just 2 slides. I will
Okay.
repeat this again. Yeah.
Yeah,
So
thank
we
you.
are going to talk about sums, products, and asymptotic. And if you have sums of products, and I just basically inform you that there will be many occasions later on, many lectures, many courses in which you will need this, including the most important among them is the analysis of algorithm. Then if you have a sum of product, then there are 3 possible solution. There are 3 possible final form of this summation of products. The first one is closed form, and this is the example of closed form solution. Yeah, for example, the sum sigma. So the notation that we'll use is sigma, summation from I is equal to 1 until ni. So basically you are summing I can move from 1 plus 2 plus 3 plus 4 plus 5 and so on until n. And this particular summation has a closed form solution. And this is the closed form solution. Namely, that this will be equal to n multiplied by n plus 1 divided by 2. Yeah, we have already discussed this before. Okay, now, but there are also summations or products that has no closed form solution. And for this, sometimes the only thing that we can do is do approximation. We will see later on in this lecture an example of this. An example of this is a Stirling formula for factorial. Factorial, you know factorial, factorial function. This is factorial function. Factorial of n is equal to 1 multiplied by 2 multiplied by 3 and so on until n minus 1 until multiplied by n. And we denote this by this notation. Yeah, notation is pi. I is equal to 1 until n. This is product. So the product from I is equal to 1 until ni. We will see later on that this is actually, it is not possible to find the closed form solution of this, but we can find the approximation of that. Now, another thing is that, well, sometimes even the approximation is not possible. Yeah, because the function is so complicated and so forth. So the only thing that we can do is to look at trend, to look at how the function behaves in the long run, how it behaves when the parameter becomes very large, for example. And you're going to see this, and this is called asymptotic notation. There are many asymptotic notation, and I'm going to cover them all in this lecture: big O, big omega, small o, small omega, and so forth. Okay, let's see first the first one, the closed form solution. I'm going to use an example. Yeah, I'm going to use an example to show how to find the closed form solution of summation. We're going to talk about annuity, the value of annuity. Annuity is a financial tool that basically pays you a fixed amount of money every year for a duration of time. Sometimes you receive an inheritance, for example, from your uncle, rich uncle, and basically your rich uncle basically gives the money to the bank and gives you an annuity for the rest of your life, for example. And this is basically one of the ways to do that. This is a financial tools that basically pays someone a fixed amount of time every year for a duration of time. So, for example, then we have annuity. We have any year M payment annuity. What does it mean? This means that uh, the bank will pay you M money, yeah, for for any years, and this is and they will give you this fixed amount of money for any year. So the question is, what is the value of an annuity? What does it mean by a value of annuity? Well, if you have a particular money right now, for example, $1,000, for example, right now. If you have a fixed amount of money right now, then the value of this money is it is right now. Yeah. So the value of this $1,000 is 1,000. But if I give you the money 1 year from now, the value of this money is not actually $1,000 anymore. Why? Because if you were to if I were to give you the money right now, you can put the money to the bank, and the bank will give you an interest. So at the end of the year, you will have, yeah, a larger amount of money. For example, assume that the interest rate is P, which is, well, just assume that this is around 8%. 8% is, of course, a large interest. The interest right now is around, I don't know. The interest right now is around 4%. 4%. Now, $10, which is invested right now, this is what it means is that if you have $10 right now and you put it in the bank, then at the end of the year, your money will be 1 plus P, the interest rate, multiplied by 10, which is equal to $10.8. This is basically the value of your money, the value of $10 after 1 year. Okay? Now, but if somebody gives you the money or $10 at the end of the year, then of course, for the time being, for this particular time, the value is not $10. Yeah? The value is not $10. So we can continue this. This money, this $10, will have value which is equal to 1 plus P to the square multiplied by 10, which is around 11.66 in 2 years, and so forth, and so forth. Now, let's look at the reverse. Yeah. So if somebody were to pay me $10, but next year, then the value right now is actually not $10. The value is equal to 1 divided by 1 plus P multiplied by 10, which is around 9.26 right now. So this is the value. This is what I mean by the value of an annuity. Yeah. So why is it like that? Because if you were to give me $9.26 right now, and I put it to the bank with interest rate P, which is equal to 8%, then 1 year from now, I will have $10. You see? So if you give me $1, $10 in the end of the year, so 1 year from now, it is just basically just the same as giving me $9.26 right now. Okay? So our goal is to determine the value of any year M payment annuity. So let's see. So you have M payment, so M dollars per year for as long as any year. The first payment is exactly right now. How much is that? M. What is the value of that? Of course, because this is basically paid right now, the value will be M. The second payment, the second payment will be 1 year from now. How much will be paid? M. Yeah? But like I said before, the value of this will not be M. The value will be equal to 1 divided by 1 plus P multiplied by M. And we can continue this. The third payment, 2 years from now, will be M, of course, and this will have value 1 divided by 1 plus P squared multiplied by M, and we can generalize this. So the ith payment will be as large as M, but the value of this will be equal to 1 divided by 1 plus P to the power of I minus 1 multiplied by M. Now we can sum them all. Look at this. This is basically the point. This is where we go to the summation. Yeah, this is where we go to the summation. Therefore, the whole value. Okay, let's continue. So the whole sum, this is basically the whole value of the annuities, then will be equal to, so this is the value of the annuity, the sum from I is equal to 1 until n. Remember the 1, this I basically represent the payment. So the first payment is right now, the second payment 1 year from now, the third payment 2 years from now, and so forth. So this is the payment. So I is equal to 1 until n, because we have n year, m divided by m. This m is basically, you can just put this out because the form is something out. Put this out, multiplied by m, something like that. 1 divided by 1 plus p to the power of I minus 1. Look at that. For the first payment, when I is equal to 1, I minus 1 will be equal to 0. So 1 divided by 1 plus p, which will be equal to 1. Yeah, which is okay. And then when I is equal to 2, this I 2 minus 1, which is equal to 1 divided by 1 plus p, is the 1. So we basically have this. This is the result of the value of the annuity. Yeah. So this is the result of the annuity. Okay. So let's continue. Now, how do we compute? Yeah. How do we compute this? Okay. I'm really sorry about that. Let's continue. So how do we compute this summation? Well, one way to do that is to try to find the closed form solution of this one. This is basically the mathematical expression that contains no summation or product anymore. This is just a formula, a mathematical formula, a completely closed mathematical formula. So let's see, how do we do this? Well, yeah. So we will transform this summation to something that we know. What do we know? What do we know is something that you have to remember this. I'll just skip first to this theorem. So it is important. This theorem is really useful for us because We are going to use this, and you will be able, you will see later on that there are many summation that can be based on this one. Okay, this is what we call the geometric sum. A geometric sum is if you sum a geometric sequence or a geometric series. A geometric series is something like this: 1, and then x squared, x to the power of 3, and so forth until x to the power of n minus 1. And there is a theorem which says that for all n more or equal to 1, so n must be at least 1. And for all x not equal to 1, pay attention to this one. This is important. X cannot be 1. Yeah? X cannot be 1. If x is exactly equal to 1, then this will have a problem, because 1 minus 1 will produce 0 here, and we cannot deal with that. Now, if this is, well, if this valid, then the summation from I is equal to 0 until n minus 1 x to the power of I is equal to 1 minus x to the power of n divided by 1 minus x. Remember this one. Now, our goal is basically to transform our previous summation to this particular form. And once we have this transformation and they are pretty close, then you will basically, you will be allowed to use this theorem. So let's return to our case. So what happens here? What happens here, this is our formula. This is our annuity. The value of our annuity is I is equal to 1 until n, m divided by 1 plus p to the power of I minus 1. What is the hope? I mean, what is our hope to transform this into this one? Well, this is basically where your creativity is important, where you have insight, where you are able to see the problem and have an imagination how to transform this into this form. Yeah? So let's look at this first. The only thing here, this is already matched actually. So we have here I is equal to 1 until n. Here I is equal to 0 until n minus 1. Well, there is a problem there, but this is okay because the index is equal to I. And then this is x to the power of I. Here we don't have x to the power of I, but this is, which is really quite strange. Also, we have actually something divided by 1 plus p to the power of, and this is basically a denominator. Yeah? So how do we deal with this? Well, let's see. The other thing is that we have here m. This m actually does not depend whatsoever on I. So basically this m can be put outside because it does not depend on I. No matter what I, m remains itself. While this component here, these terms here, this depend on I. Okay, so it doesn't matter. So let's see first. Yeah, first we will try to transform it and to match the boundary. Let's try to match the boundary. The boundary here is from I is equal to 1 until n, while the boundary here is from I is equal to 0 until n minus 1. How do we do that? This is easy, because if this is n and this is I plus 1, we can just substitute. Take, for example, j. J is equal to I minus 1. So if j is equal to I minus 1, then when I is equal to 1, then j will be equal to 0. When I is equal to n, pay attention to this one. When this is n, then j will be equal to n minus 1. So you see, just by performing this substitution, we have this formula. And this formula is just the same as the previous one. The sum from j is equal to 0 until n minus 1, m divided by 1 plus p to the power of j. Why do we have here to the power of j? Because we substitute j is equal to I minus 1. This is I minus 1, so the whole thing becomes j. You see? So this is okay right now. Now, and we are getting closer to this form. But this is not enough. It is not enough yet. So what we have right now? put this m the front, because this is basically just a multiplication. Every time we multiply it by m, let's put it out because it does not depend on j or I. So we put it out here. And then if you put this out, then the whole thing will be 1 divided by 1 plus p to the power of j. Yeah? And 1 divided by 1 plus p to the power of j is equal to 1 divided by 1 plus p, the whole thing to the power of j. So basically, I will substitute this 1 divided by 1 plus p to the power of j, yeah? Well, there is no to the power of j, 1 divided by 1 plus p with x. So if I substitute x is equal to 1 divided by 1 plus p, then the whole thing becomes the summation of j plus 0 until n minus 1, x to the power of j. Remember, look at this x. X is equal to 1 divided by 1 plus p. Yeah? Okay, let's continue. Now, once you have this is basically, you can just use this one. This is exactly this theorem. Right? This is why I told you before that it is really important for you to remember this theorem and to be able to transform this theorem to any problem whatsoever. Yeah? Okay. Now then, we can continue with our closed form solution. This is our formula right now. Once we transform it, j is equal to 0 until n minus 1, x to the power of j. According to this theorem, the whole thing becomes 1 minus x to the power of n divided by 1 minus x. Look at this, that x cannot be equal to 1, but we have already ensured that 1 divided by 1 plus p cannot be equal to 1. Yeah? So, then this summation, you see, this is what we mean by a closed form solution. This summation has a closed form solution. You can just replace this by 1 minus x to the power of n divided by 1 minus x. Yeah? And you can replace again. What is x? X is our substitution. X is equal to 1 divided by 1 plus p. So you can replace them, and the final formula is this one. M multiplied by 1 plus p minus 1 divided by 1 plus p to the power of n minus 1 divided by p. So if you know p, if you know m, if you know n, then you know right away. You don't have to perform this summation one items by one item. Yeah, you can just use this formula to find that. So this is basically yeah, this is basically our example. So let's see whether we understand this. Let's say that someone asks you this one. I'll give you an annuity. This annuity is basically a moment. Assume that you have you won a lottery, and this lottery basically will give you right away money about $750,000. This is lottery. $750,000. And then they also offer you the second alternative. The second alternative is, instead of giving you right away $750,000, they will give you an annuity of $100,000 for 10 years. Yeah, for 10 years. So the question is, well, will you accept it or not? And you, of course, because of this, the thing that we have already seen, you will be able right now to compute this. Yeah, you will be able to compute this. So if you compute this, yeah, if you compute this will be, well, our M will be equal to $100,000, okay, and then our N will be equal to 10 years. Assume that P is equal to 0.08, similar to our, yeah, similar to our, what do you call this, our example, our previous example. So you can compute it yourself. Yeah, you can compute it yourself. So the formula will be, I'll just compute it here. Excuse me. So this will be formula. This will be equal to this M here. Yeah, multiplied by 1 plus 0.08 minus our, yeah, this one is 1 divided by 1 plus 0.08, okay. This is n minus 1, so n minus 1 is 9, okay. Whole thing is that, and this one will be divided by 0.08. Excuse me. Why is it a minus? So this is it. So this is the result. Yeah. So the result, if you compute this, the result will be 724,688 point something. So you see the value of this annuity, the value of $100,000 for 10 years annuity is actually less than this one, less than $750,000. So if they offer you this one, then it is wiser actually to just go for the cash instead of going to the annuity, because the value of this annuity, if you compute them, is actually, yeah, below the summation of this cash. Okay, but let's continue. Well, if you have any questions, you can always ask me right away. So let's continue. Well, that is annuity, but the problem is, what if somebody asks you? What if somebody asks you a question like this? Uh, what is the offer is not for 10 years, but forever? Yeah. What if the offer is not $100,000 for 10 years, but the offer from the lottery basically will give you an annuity of $100,000 forever? What does it mean forever? Forever. Yeah. As long as the whole world is there, they will give you $100,000 every year. Well, what if you are dead? Well, you're dead, and your grandchildren, your children, they will receive $100,000 every year. I mean, you will Will you take that, or instead of the $700,000, or well, let's say that I'm going to change this a little bit. I'm going to say, what if this $1 million? I'll give you $1 million right away, or I'll give you $100,000 forever. Yeah. So which one do you choose? Let's see. So this is actually an interesting question, and in annuity, you should be able to look at these also. You should be able to compute this. So let's see. Uh, Actually, there is another theorem which is also has something to do with this geometric sum, which is called infinite geometric sum. Look at this. In infinite geometric sum, if the absolute value of x is less than 1, look at this is important. So x must be less than 1. It cannot be more than 1. In this previous one, x is allowed to have value something larger than 1, as long as it's not equal to 1. X is allowed to have value larger than 1. But in this one, x must be smaller than 1. If the absolute value of x is smaller than 1, then according to this theorem, the summation from I is equal to 0 until infinity, look at this, until infinity, x to the power of I is equal to 1 divided by 1 minus x. So how do we get this? Yeah, how do we get this theorem? And this theorem is actually quite easy. If we go back to this theorem, if n here is enlarged, increased again and again, this n becomes larger and larger, larger, larger until this is close to infinity, then this one will be 1 minus x to the power of n. And this n will be larger, larger, larger. But because this x here is smaller than 1, then this will be smaller and smaller and smaller and smaller and approaching 0. So if these things approach 0, so when n approach infinity, then x to the power of n will approach 0. So the only thing left is 1 divided by 1 minus x. Yeah. So this is basically our theorem. How do we use this? We can use this also to compute about our infinite annuity. Look back again to our annuity. If this is forever, this annuity is forever, then the j is equal to 0 until infinity here. Yeah. So we can go up until infinity, and we can compute this. We can compute this according to this one. Then this will be equal to m multiplied by 1 divided by 1 minus x. You just have to substitute x by 1 divided by 1 plus p and so forth, and this is the result. The final result is m multiplied by 1 plus p divided by p. Yeah, even for infinity, we are actually able to solve this in a closed form solution. Okay, now let's try to compute this. Let's try to calculate this one. Okay, now if this is forever, then the formula will be around m. You remember the formula, m $100,000, yeah, multiplied by 1 plus p, 1 plus 0.08 divided by p divided by 0.08. Huh? So this is the result. This is the result. Yeah. So the result is $1,350,000. So if this is forever, then it is actually better to take this forever because this is larger than this one. Yeah, this is larger than this one. So if you have this annuity and then let me see. $100,000 multiplied by 1 plus 0.08 divided by 0.08 is $1,350,000. But this is better than this one. Yeah. So, but if they offer you something larger, for example, in this one, if they offer you $1.5 million, for example, and it's, of course, it's important to take this one. So, why is it, for example, let me take an example. This is, for example, $1.5 million. Yeah. How can it be that this one is larger than this one while this takes forever? It is actually quite easy. It is actually quite easy to think about this one. To think about this one is, well, if the lottery gives you $1.5 million in one shot, you can just actually put it in your bank. Yeah, put this one in your bank. If you put this in your bank and the interest rate is 0.08, then in 1 year you will receive interest this much, 0.08. Yeah, this month, $120,000. So from the interest alone, you are actually receive something larger than this annuity. So if the lottery gives you this money right away, put it in the bank, and you will receive every year an amount of money which is larger than the annuity. That's why it is, even though this is forever here, this is better than this forever. Okay? So I hope that if you have any question right now, you can ask me. If not, then we will take a break. I think for 2 minutes. Yeah, and then I'm going to continue uh, with the next topic. Okay, let's continue then. So we are able to find a closed form solution of something. So what is the general formula, how the general technique for us to find the closed form solution of some summation, for example? Well, we're going to talk about this later on. So let's just continue right now by looking at other types of summation. There are other types of summation. Sometimes the form of the summation can be solved by looking at the derivative or the integral of the geometric sum. And it is important for you to have this insight, to have this capability, to have this imagination. Look at the formula and imagine how it look like. Yeah. So, for example, look at this one. This one, well, previously we have seen a summation of the form x to the power of I. What if somebody asks us this formula, for example? The summation from I is equal to 1 until n, I multiplied by x to the power of I. Well, we don't have any theorem about this one, but if you see, this is actually quite similar to what we have seen. And right now, you can use any mathematical manipulation that you have already seen. For example, derivative. Yeah, if you remember, the derivative of x to the power of I, what is the derivative of x to the power of I? Well, the derivative of x to the power of I is, well, this I here, you will assume right away that this one, yeah? So let me continue. This one. What is the derivative of this one, for example, x to the power of I? Well, from calculus, you know that the derivative of x to the power of I is something like, well, you move this I to the front. So I multiplied by x, but then this power is reduced by 1. So I multiplied by x to the power of I minus 1. You see? So we have actually some sort of a formula. So and if you take this derivative, because this is a sum, this basically just taking the derivative of each one of them. So if you take the derivative of each one of them here, this is just equal to taking the derivative of this one. Yeah. So this is basically the idea. So let me continue with this. Somebody asks you, what is the formula for this? What is the closed form solution of x is equal to 1 until n I x to the power of I x to the power of I, this summation is equal to x plus 2x to the square plus 3x to the power of 3 and so forth until n x to the power of n. How do we do this? So this is what I mean by you have to be able to look at ways to manipulate this summation. And during the exam, I may ask you something completely different. Perhaps it is not it is not it is not achievable by derivative, but from integral and so forth. So, but let's look for this particular example. Take the derivative of this one. Yeah. So I will just take as our base this summation here. This summation is summation from I is equal to 0 until n minus 1 x to the power of I is equal to 1 minus x to the power of n divided by 1 minus x. And then I take the derivative of that one. The derivative d divided by dx of this summation here, x to the power of n. Well, what about this one? Here we end up at n, while in the previous theorem we end up at n minus 1. This is actually easy. It is easy because what? If we end up here with n and the previous one we end up at n minus 1, just replace n minus 1 by n, then the whole thing will be just the same. This is the beauty of summation. Yeah, summation, if you basically replaceable. If you find an m for example, a variable there, replace it with something, you substitute it with something, then the whole thing is still valid. So this will be 1 minus x to the power of n plus 1 divided by 1 minus x. So we have here a summation. If you take the derivative of the left one, this will be the same as the derivative of the right one. Yeah, so this is basically an easy calculus. If you have x is equal to y, then the derivative of x will be equal to the derivative of y. Yeah. So let's continue. What is the derivative of this one? The derivative of this one is the summation of I is equal to 0 until n. I, like I said before, I multiplied by x to the power of I minus 1. What about the derivative of this one? You remember the derivative of u divided by x. Yeah? You remember the derivative of u divided by x. I hope you remember that. So, wait a moment. I will give you. Formula for that. Look at this one. So the derivative of f divided by g, this one, the derivative of f divided by g is the derivative of f multiplied by g minus the derivative of g multiplied by f divided by g to the power of 2. I just have to remember this one. Yeah. So usually in calculus class, you change this into u divided by v. Yeah. The derivative of u divided by v is equal to the derivative of u multiplied by v minus the derivative of v multiplied by u divided by phi squared. So let's return to our slide. So the derivative of this, the whole thing here, then the derivative of this one first. Look at this. What is the derivative of this one? The derivative of this one is n plus 1 multiplied by x to the power of n minus, because this is 1 minus. So minus n plus 1 multiplied by x to the power of n. This is the derivative of this one. Multiplied by 1 minus x. Multiplied by 1 minus x. Then The other one is the derivative of this one. What is the derivative of this one? This derivative of this one is minus 1. Minus 1 multiplied by u here, 1 minus x to the power of n plus 1, divided by 1 plus minus x to the power of 2, this one. So phi squared. So the only thing that is left for you to do is just to simplify this thing. And you can simplify it. Yeah? A moment. So if you simplify them, then the result will be 1 minus n plus 1 multiplied by x to the power of n plus n x to the power of n plus 1 divided by 1 minus x to the power of 2. And we are almost there. The problem is right now that there are still two things that are missing. The first one is the boundary. The boundary that is asked here is I is equal to 1, while here is I is equal to 0. The second one is we are asked here basically to find, to find the solution of summation of I multiplied by x to the power of I, while here this I multiplied by x to the power of I minus 1. So what do we do? This is actually easy. Let's look at the second problem first. The second problem is x to the power of I minus 1, while we are asked actually x to the power of I. How do we do that? This is easy. You just have to multiply this one by x. If you multiply the whole thing here by x, then this will becomes x to the power of I. So if you multiply this left hand by x, what do you have to do? Well, all you have to do is just multiply this right hand side, every one of them also by x, and we are done. Yeah, you see, multiply this by x, multiplied also on the right side, by an x. So you see, here is 1 minus x to n plus 1 to the power of n multiplied by x to the power of n, and this becomes x minus n plus 1, yeah, multiplied by x to the power of n plus 1, x to the power of n, and this one become n x to the power of n plus 2 here. Yeah, so this is completely, we have this. What about the boundary? What about the boundary here? The boundary here is starting from I is equal to 0. I is equal to 0. While here, I is equal to 1. So what can we do? This is actually easy. If you start from I is equal to 0, then this I will become 0. So there is no element when I is equal to 0, because the whole thing is becomes 0. You see? The whole thing here becomes 0 when I is equal to 0. Here also, when you start here from I is equal to 0, then this thing here becomes 0. So it doesn't really matter whether you start from I is equal to 0 or you start from I is equal to 1. So, so there is no difference. So this is the result. Yeah? So this is the result. You see right now that by just by looking at this one, yeah, just by looking at by performing some sort of manipulation, we are actually able, yeah, we are actually able to find the closed form solution of this one. So to conclude, if you see a summation and there is an x something to the power of the index, look at this. This I is the index. Something to the power of the index. You have to remember, oh, I will be able to solve this by using the geometric sum. Yeah. Now, sometimes the summation can be a little bit complex, can be a little bit involved. Don't be afraid. you have to be able, you just have to look at how to manipulate them. Look at how to use, for example, derivative or integral and so forth to solve it. Okay? Now, this is something to the power of the index. We will see later on. What about the index to the power of something? Then this is completely different. If the index is to the power of something, then this is called basically a polynomial. We will see about polynomial later on. Okay. Now, you know right now the summation from I is equal to 1 until ni multiplied by x to the power of I. What about if we change this n to infinity? If you change this n to infinity, this is the result. If the absolute of x is less than 1, then the summation of I is equal to 1 until infinity I multiplied by x to the power of I is equal to this one. How do I have this one? Yeah? How do I have this one? This is actually easy. Change this approaching infinity, n approaching infinity. When n approaches infinity, then this one here approaches 0. This one approaches 0. This one also approaches 0. So if you, even though n is large, but this is smaller. So the whole thing here approaches 0. The only thing left is equal to x divided by 1 minus x to the power of 2. Okay? So